might be interesting. I'm going to talk about a lot of the research I do on visualizing uncertainty, which I think is kind of a challenging data viz problem, and try to talk about it a bit from the perceptual side as well. What we know about sort of how well people can read common uncertainty visualizations. So to get started, I probably don't have to tell most of you that, visualizations are used all the time to support different types of decisions and inform the public. And they play, I think, this important role where people look to visualizations to form impressions about, what they should believe about the true state of the world, which data are proxies for. So one example, of course, would be something like, election forecast predictions. Here we're seeing predictions of vote share from 538's model for 2020. These are based on, poll results. They're based on historical data on past elections, many types of assumptions. But this data or these model predictions are intended to capture, what we should expect to see in the election, given everything we know to date. And so we could assume, this is our best possible estimate of what we should believe about the true vote share. But of course, most of the data we visualize is subject to some uncertainty. And we can quantify that uncertainty in some cases, in particular here, we have uncertainty about the amount of actual support for each candidate, since we haven't really asked everyone in the country their opinion. But we also have unquantified uncertainty, like, how good Nate Silver's prediction is about just how much economic uncertainty COVID contributes, which is kind of hard to quantify. And so if we think about how visualizations can convey that data is uncertain or that data is approximate, this visualization, I think, does a decent job of that because we see at least these kind of shaded bands here. So we know that it may be, the vote share for Biden's not exactly 53%. It could be more, it could be less, but I think it could be better as well. And so today I'll try to talk through what's a better way to express this type of information. But before I do that, I just want to point out something that you may have noticed, but maybe not acutely, which is that in many domains beyond election forecasting, presenting uncertainty at all when we convey data is generally not the norm. And if you think about, how often you see visualizations of estimates, averages, et cetera, that are subject to uncertainty, but you see them without any acknowledgement of that, it's quite striking, how comfortable we seem to feel, just not really acknowledging the sort of limitations of our knowledge. And we have extremes, like the Congressional Budget Office, which doesn't publish uncertainty with their estimates very often at all. So they're making, estimates into the future at the levels of trillions of dollars. And I guess we're just supposed to assume that these are very precise estimates. And then we also have organizations like Pew, which are going to be a little bit more responsible. So here Pew's showing a visualization of predicted number of unauthorized immigrants in different cities. And if you scroll down the page with the article that comes with this, you'll see things like, well, not all the differences you see in this visualization will necessarily be reliable. There's uncertainty. But one of the problems, even when authors try to convey uncertainty, many times, it is hidden. It's not front and center. People look at a visualization and they might not take into account, the limitations that the authors are trying to stress. And so there's a lot of times, when uncertainty is de-emphasized, I would say. And even in science, where we could say it's primarily about the study and discussion of uncertainty, we see similar tendencies to sort of suppress uncertainty or at least not emphasize it, to dichotomize results and think about things like statistical significance, which sort of suppresses this idea of variation. And there's a lot of reasons I think that authors don't want to convey uncertainty. So, I think it's a deep issue, embroiled in incentives and norms around communication. Many of the rationales that people cite sort of overlap even in different domains. So things like, you don't want to burden the user. It's cognitively difficult to think about uncertainty. They might not understand it. It might not be essential to their task. So why bother? There's also fears, I think, that authors have related to, not wanting to appear confident in their own estimates of uncertainty. So it's hard to calculate uncertainty sometimes, and you don't want to seem like you know more than you do, so you just leave it off. And there's also these concerns that, nobody else is conveying uncertainty very transparently with their estimates. So why should I? It'll just make me look worse. And I actually talked to authors in one study and heard all of these things. I talked to, some famous data journalists, some famous designers. The sort of issues I want to talk most about today are sort of some of these more technical problems, things like it's hard to calculate, and there's a lack really of good visual techniques to show it. It's also hard to evaluate, even if you convey uncertainty visually, whether you did a good job or not, because it's often hard to state like what is the goal exactly of conveying uncertainty. So I'll talk a little bit about how to better visualize it, and as well how to evaluate. So I'm going to start with how we currently sort of visualize uncertainty, at least by convention. And when I say uncertainty here, I mean really distribution of some form. So you have some underlying distribution. It might be a measurement distribution. It might be a sampling distribution, but you want to convey that to a viewer. And I would argue that we lack many easily interpretable, sort of generalizable methods for conveying uncertainty. And by generalizable, I mean methods that we can apply widely to different types of charts or different underlying geometries in different visualizations. So we can roughly categorize existing methods for visualizing uncertainty or probability distribution as mostly static, so not dynamic or animated. And they usually use either summary marks, so things like error bars, or other graphical annotations to represent moments of a distribution, or statistical constructs like confidence intervals, or they will actually map a probability value or maybe a confidence value of some type to what we would call a visual variable or a visual channel in a visualization. So things like height in a density plot, or area or width in a violin plot, or opacity in a gradient plot. And both of these types of approaches that we conventionally see used have some issues when we look at them using sort of standard visualization research criteria that we use to judge how effective a visualization is. So one problem, especially that we see with summary marks like error bars, is that they violate this criteria we call expressiveness in visualization research. And expressiveness, it has a formal definition, but the sort of kind of common language way to understand it is that we want to choose visual encodings that express the data such that, when somebody looks at that visualization, their natural spontaneous interpretation is correct about what's actually in the data. And so sort of a really obvious, violation of expressiveness would be something like, having two-dimensional categorical data, so car models and where they were made, what nationality, but expressing that in something like a bar chart that uses length or really position, because we have a common scale to show that data. So if you visualize categorical data this way, you end up with people thinking things like, oh, Sweden's Volvo 260 is somehow more than, Germany's Vita Dasher, which isn't actually supported in the data. There's no numeric estimates here. Another example of expressiveness, this sort of a violation of expressiveness that we see a lot in charts, relates to things like using color to convey continuous values. So in a lot of scientific visualizations, we'll see rainbow color scales still. And one of the problems there is that, we're trying to express a quantitative continuous variable, but the way that we perceive hue is not continuous. It depends on where we are in the underlying sort of scale of wavelengths. So to demonstrate, you could say I have 2 points in a visualization where I'm using color, maybe it's a map. And both of the points that I'm trying to compare fall in, this little red area, which is a certain range in terms of wavelength. It's going to be much harder for me to see any difference between those than it is for me to see a difference, if the same distance of points happen to be over here and cross this kind of blue-green color divide. So these are all violations of sort of this expressiveness criteria. So going back to uncertainty visualizations, how does this apply? Well, often when people look at some of these summary mark visualizations in particular, they believe things that are not really true about the underlying distribution. So one issue with error bars, which maybe you've noticed before, is that they can mean lots of different things. So they can mean 95% confidence interval. They can mean, a range showing standard error, showing standard deviation. In all of these cases, they look exactly the same. And so some people will see something like an error bar and think, oh, it's a uniform probability range because to some people, that's what it looks like. But only in some cases, only under certain definitions is that true. And in particular, a 95% confidence interval in a frequentist paradigm should be interpreted in sort of a uniform probability way. But there's lots of other reasons people don't understand confidence intervals that go far beyond that. In a lot of other cases, we have something like a normal distribution, and it's not true that any of these values is equally probable. Another error that we see other people make, which has been estimated to be about 30% of lay people reading error bars, based on studies that have been done, is that they'll see an error bar and they'll think the range of values that falls on top of the bar encoding the mean is more probable than the range that falls above, that's not on top of the bar. And this is called within the bar bias. And again, it affects some number of people often, and you can't really blame them because it does look like there's something different about the bottom of the bar when you have a bar, an error bar on a bar encoding something like an average. Another issue that we see is that people rely on sort of these visual cues when they're faced with things like error bars to judge properties like effect size. So in another study, we found that people will rely on how big the difference in means looks in a chart in order to judge the effect size, which is basically the size of the difference in means, but accounting for the variance in each group. So we ran a study where people saw either they saw the same underlying data, a study where there was a control and an intervention basically, but they either saw error bars that represented basically confidence intervals, so the mean plus or minus 2 standard error, which is the standard deviation of the sampling distribution describing the uncertainty in our estimate of the mean. Or they saw error bars that represented what we could call containment or a prediction interval, which is the mean plus or minus 2 times the standard deviation. People also, regardless of what visualization they saw, they got the information on the other conditions. So they got all the information in both conditions, but they got some of it in text and some of it visually. But what we found was that depending on what we visualized, people had very different beliefs about the underlying effect size. So they saw this was a much bigger effect than this one, simply based on on what the visualization emphasized. So these are all sort of expressiveness violations because people see things in a visualization and their spontaneous interpretation is that that's meaningful about the data that they're seeing, and it's not always the case. So summary marks have some issues. On the other hand, I said we can also use visual variables, so map things like probability to properties of a visual mark. And these have less issues usually with expressiveness because they're showing you more information for one, and there's less of these sort of spontaneous errors. But we run into problems when it comes to another common criteria we use in visualization research, which we call effectiveness. And effectiveness, sort of put simply, is like that we care about how well people can read the values from the visualization. So, to give you an example of how different visualizations can make perception harder or easier, we can do a little test where, I ask you, how much less blurry is B than A here? I've mapped probability to blur level. So that should feel pretty hard if you're trying to actually do this. And the answer is actually 3 times, but not many people get that because this is just extremely hard to read. We could instead try to map it to what we call value or lightness. And I could ask you how much darker is B than A here. Still pretty hard. This time it's 2 times. I could ask you to judge circular area. So how much bigger is B than A? Maybe slightly easier, but still a lot of variance here, usually between people. So here the answer is 5 times. Or I could ask you, how much longer is B than A, which is actually not even a length judgment. All you have to do is compare the difference in position because we have a common axis here. And this should feel much easier to you. And that's because we know from a bunch of graphical perception experiments that mapping data to position or length, so things like scatter plots, bar charts, stacked bar charts, people are much better at actually reading the data from those encodings than they are from things like circular area or aspects of color. And so this is problematic because often when we're trying to map something like probability to visual variables or visual properties of marks, we've already used the more effective encodings, things like position, to show whatever the underlying data value is. So, maybe it's heights or weights. We're already using position in some cases, along Y here, and we're left with these less effective encodings, things like opacity to show probability. Even when we're using position, so here, you could say a density plot or a histogram is using X position for the values and then height or Y position for the probability. But the problem we run into even in cases like this is that when we're dealing with distribution, we often care about things like one-sided probability intervals or two-sided probability intervals. And so we end up having to make area judgments, which are not as effective. And so in particular, something that I think is unfortunate is that many people will gravitate when they're trying to visualize uncertainty to these visual encodings that sort of look like uncertainty. So things like gradient plots can be popular because, differences in opacity or differences in blur level look like uncertainty. So semantically, it makes sense. But unfortunately, some of these are extremely hard for people to quantify. So if I asked you to sort of judge the difference in probability between a point like right here and a point like right here, you'd probably not be very good at it. So that sort of defeats the purpose of visualization to begin with. But I think this doesn't mean that we can't use things like opacity or color to show probability in some cases. I think we just have to be extremely careful. So metaphors do matter, and sometimes encodings that look like uncertainty can still be useful. But I would try to reserve them always for things like just a couple different categories or ordinal data where you have sort of a ranking and you don't have a lot of groups. So the Economist did this in their election forecast. They used color or hue, basically red or blue, to show support for Biden versus Trump. But then they used how dark the color is, or what we would call lightness or value, to map to probability. But they discretized the probability, and which kind of makes sense because you're not going to be able to see differences very well between all of these, if you had a continuous scale, from blue to red. But even better than this, I would say, because you're sort of throwing out information here, would be to just reserve these encodings that look like uncertainty, like value or lightness, for information that people don't need to quantitatively make estimates about at all. So I like, for instance, how Bank of England sometimes uses lightness, where here, they have the more recent month gets the darker color, but we know that we don't have to make, precise quantitative estimates of how different February is from March or April. So it kind of works. It gives the right impression of like the more recent data is more useful, but without these perceptual problems. So I want to talk about ways to visualize uncertainty that can be better. But first, I want to talk about sort of this deeper problem that we run into when we try to make better visualizations, or just when we try to visualize uncertainty at all, which is the nature of probability itself. So to quote a famous actuary and statistician, Bruno Di Finetti, the problem with probability is that it doesn't exist. And I think what he means there is that probability exists kind of only within our minds. For example, if we're looking at something like the top level 538 forecast from 2016, we get these percentages, which are basically probabilities, like 28.6 chance of Trump winning. But what does that really mean? In the actual world, events that we describe probabilities for will either happen or they won't. So there's no clear way to interpret what this 28.6% means. And even among statisticians, there's some disagreement. So a frequentist would say this is a long range frequency, and that's how we should think about it. A Bayesian might differ about that. And so probability is complex. It's not clear what it always means. And so I think facing a probability, we see people sort of try to simplify their decision. And so one way would be, for instance, rounding up. So I think in particular in 538's 2016 forecast, where we saw these percentages right at the top of the page, a lot of people just rounded up. They said 70 is different enough from 50 that I'm just going to treat it like 100%. So this makes uncertainty, just dealing with uncertainty and conveying probability, very hard. But one kind of trick that we've been using in my lab to apply to visualization actually comes from cognitive psychology. And this is just that if you want to help someone reason better with a probability, including things like reasoning about conditional probability, you should just take it and re-express it as a frequency. So rather than saying, 30% of the time, you should say 3 out of 10 times this happens. And there's some research showing that if you're, in particular, you're doing these sort of classic Bayesian reasoning problems, things like figuring out what's the chance that you actually have a disease because you got a positive test result, given what you know about the prevalence of the disease in the population and the accuracy of the test, people, when they're given frequencies, will actually come to more accurate answers on these kind of tasks. And one reason I think this might work is that if we think about sort of how we experience probability in the world, it often is in terms of a frequency, or that's how we can most easily relate to it. So, if I want to think about what's the probability that I miss my train if I get to the stop at a certain time each day, I might think, well, in a given week, if I get to the stop at that time, I expect to miss the train maybe once out of 5 times because it came early. So this is sort of a natural way to think about it. And, in my lab, we've been looking at how to apply this to visualizations, but we're not really the only ones. So I've been, working with frequency-based uncertainty visualizations for a while. And while I'd like to think that, like the media is catching on and learning from me, I don't know that that's the case. Journalists have also been experimenting with things like using frequency framing, even in visualization. So there was a lot of changes in the election forecasts, how they were conveyed, that I noticed between just 2016 and 2020. So in 2020, both The Economist and 538 gave top level information about chances of winning in terms of frequencies. And 538 even visualized sort of different hypothetical outcomes you could get if you ran the election over and over using frequency. So they had this sort of ball swarm, as they called it, where you can actually basically, I think it's designed to give you a better sense of, what something like 27% chance means. You can actually imagine, oh, there are worlds in which Trump wins. And so in my lab, like I said, we work on sort of studying visualizations like this and coming up with visualizations like this. And, it might seem like this is sort of a small trick. Like, how does this sort of frequency framing in a visualization really change things? But that's the kind of thing that we look at, is just how much does this help and in what contexts? And so some of the research collaborators and I have done, in particular, a collaborator, Matt Kay, who I work with a lot on uncertainty visualization, we've looked at certain domains and designed frequency-based visualizations and then tested how much they help people make, say, decisions or probability estimates in that domain. So one domain that we looked at originally was people making decisions related to transit. So a lot of people use these apps that show them things like bus arrival times or predicted train arrival times. And often these interfaces for these apps will show you just a point estimate of when your bus or train is going to arrive. But this is really frustrating to people who use these apps because they know that these point estimates are not always going to describe what happens. So sometimes trains or buses come early, sometimes they're late. And so what we did is take a popular bus arrival time app in Seattle and get historical data and GPS data and basically create a distribution so that when we get a point estimate of something like this bus on this route is coming in 2 minutes, we can actually represent that with a distribution. But we wanted to test, what happens if we represent it with something like a density plot, this kind of smooth continuous representation, versus something that shows probability in terms of frequency. So we designed what we call a quantile dot plot, kind of similar to the 538 ball swarm plot that I just showed you. But here we have a continuous outcome rather than just a binary event. And so we want to represent that with some number of dots. And so we can choose ahead of time how many dots do we want. In this case, we have 20. And then we're going to sample from the quantiles of the distribution so that we get sort of a representative depiction of a distribution each time. This is not actually the quantile dot plot for this particular distribution, I should add. That's a little confusing. So anyway, so we created this technique, and then we wanted to study how much does it seem to help people in this domain of making transit judgments and decisions. And in particular, we were curious, what's a good number of dots in something like this? Because the more dots you use to represent the distribution, the more precise your representation is. But at the same time, the more dots you use, the more sort of cumbersome it might be for someone to try to actually do something like count the dots. And so you might end up with a visualization, say if you have like 100 dots, where someone just defaults to doing area judgments, which is what we're trying to kind of get away from. And so we wanted to ask this question about, how many dots make sense, or do people do well with, and also just, how do they do when we compare something like a quantile dot plot, a frequency plot, to something like a continuous density plot. One of the challenges we always run into in our research is that it is hard to evaluate when an uncertainty visualization is actually really helpful. And there's a lot of reasons this is hard. So one is that, sometimes the ideal outcome or decision from an uncertainty visualization is hard to define. Sometimes it's going to vary person to person because different people have different, risk tolerances, et cetera. So we have to think about that. There's also no guarantee that some of the standard measures we use in visualization, like how well did someone, read the data, is going to translate into using it in a decision, especially with uncertainty or probability information, where people often, they can tell you what they see when you ask them, but they will not necessarily use it because they'll try to suppress it in real life because it's complicated. And finally, there's because of all this sort of tendency to suppress uncertainty in judgment, you can end up with cases where if you ask people what visualization they prefer to use, they'll choose one that's actually less effective for decision making because it feels more comfortable to them. And so we have to sort of grapple with all of this. And I've even written papers on sort of, how hard it is to evaluate uncertainty visualizations. But in most of the cases we study, we'll try to, because of these challenges, use a few different techniques. And so that's what we did with these quantile dot plots when we were thinking about bus arrival time estimates. So what we did first was did a study with actual bus riders in the Seattle area, where we mocked up little transit app displays, and we assigned people to different visualizations. So either a dot plot with 20 dots, a dot plot with 100 dots, a density plot, or what we call a stripe plot, which is basically 100 draws shown as stripes. And then we asked them in this first study just to make probability estimates about their chances of missing or catching the bus if they got to the stop at various times. What we found here in this initial study was that the dot plots with 20 dots seemed to do better than the other visualizations, including the 100 dot plots. And we reason that maybe that's because it's easier, especially in this kind of domain where you care about one-sided probability intervals, like what's my chance of missing the bus, to sort of quickly count small numbers of dots. And in particular, people were more consistent. So you can see sort of the average kind of amount of bias here between the different conditions. These are model estimates based on the data we collected, but people were more consistent within a person and between people in sort of how they estimated probabilities. But like I said, just because people can perceive information better with an uncertainty visualization doesn't mean that they can actually use it in decisions. And so in a second study, we actually wanted to look at incentivized decisions. So in this, because we were thinking about busing, we actually set up a decision study where we had people make these kind of realistic decisions under, particular incentives that we tried to learn from real bus riders, where basically they saw an uncertainty visualization. These are all the different ones we tested here. And they had to decide when they would go to the bus stop, and they got paid more if they caught the bus, but they also got penalized for waiting too long at the bus stop, et cetera. And so we tested quantile dot plots with 20 dots, with 50 dots, cumulative density functions, which often, I think the average person doesn't understand at all. But in this case, we thought might be useful because they're good at showing a one-sided probability. We also tested intervals. We tested density plots with intervals, as well as different text expressions of one-sided intervals with different levels of confidence. So I'm going to skip all the detailed model results here and most of the things I talk about today, just because it gets pretty tedious and I don't have time for all of it. But just kind of high level summary of the results. Here we found that the dot plots and the CDFs did best. The dot plots with 50 dots were slightly better. this was a study where people made repeated decisions and they got feedback, so we could look at sort of how well they learned how to make better decisions with different uncertainty visualizations. And so with the dot plots and the CDFs, they started off pretty accurate and then they got better in terms of decision quality. Intervals, people did not do well with at first, but they tended to at least improve over time, so that was good. Densities were similar to that. But text expressions were really unpredictable. So I think we saw that if you expressed whatever the 99% one-sided probability interval, people actually did reasonably well, not as well as they did with some of the dot plots in the CDF, but they did okay. But then if you express something like an 85% interval in text, people were awful. They couldn't really learn. They started off pretty badly and they just stayed there. So I think that that's really a function of sort of people can kind of think about certain levels of confidence, but others like 85% are just really difficult. But we'd have to do more studies, to really know for sure what was going on there. So quantile dot plots, we found, the simple frequency trick seems to work pretty well, at least at improving perception slightly and then improving decisions. But there's a challenge that doesn't really get captured by the studies that I just showed you, where we're just asking people to think about a single distribution at once, which is that, often we care when we look at visualizations of uncertainty about making what we would call effect size judgments, where we're comparing a couple different uncertain quantities or a couple different probability distributions. And so, effect size, again, is this idea of how big is the difference, but accounting for the uncertainty in each group. And we can think about effect size in different ways. So, say we've run an experiment where we had a control and a treatment. The treatment is in blue here, or our intervention, the control's in green. So, we could ask, well, what's the probability if I repeated my study many times that I would still see that the intervention is better? This is one way of expressing effect size, called probability of superiority, or common language effect size. But if we ask people this kind of to make this kind of judgment with visualizations of uncertainty, including even potentially frequency-based uncertainty visualizations like quantile dot plots, there's this potential risk, which is that this is a really hard judgment to make from any static visualization. And so people might rely on what we would call heuristics, or sort of simple visual proxies. And in particular, if you don't know sort of statistics well enough to actually calculate this probability of superiority, given what you know about, the independence of the distributions, one easy thing to look at instead is sort of how big is the difference in means. And what we found in a study I did is that when given things like error bars, violin plots, people will in fact, and asking them this question, people will in fact appear to substitute the size of the difference in means for how big they think this effect size is, or this probability of superiority. So with a big difference in means, regardless of the variance, people tend to say it's a high probability difference, and with a smaller difference in means, it's low. But of course, this is kind of a problematic heuristic, because it also matters, how much uncertainty you have. You can have a big difference in means, but a lot of variation in each group, for instance. So this is a really hard sort of heuristic or type of strategy to design against when you're dealing with uncertainty visualization, because people will do this and they don't even always know that they're doing it. And so an initial when I was thinking about sort of how to get around this type of problem in designing uncertainty visualization, something that I came up with a while back was what I call hypothetical outcome plots, where we're not even going to use a static visualization because people are too good at sort of extracting the mean and then just comparing that. And instead, we're actually going to draw random samples from each distribution and show one at a time in an animation. And so this way, people actually have to sort of contend with the uncertainty, because you can't watch the visualization or make any estimates without sort of accounting for uncertainty, because it's baked in, it's sort of intrinsic. And so, this is, an interesting technique that's actually pretty generalizable. You can apply it to many different charts, but it seems kind of jarring, I think, to many people, because, you're actually supposed to focus on these moving lines, or the actual visualization is moving. And so initially we did a study to see, well, how bad is this? So if we have people look at distributions, and initially, we'll show them just a single distribution and animate it. So imagine just one of these lines. And we'll ask them things like, what's the mean of this distribution, or what's the probability that the value of this random variable is going to be above or below some amount. What we found was that people actually, to our surprise, did comparably well compared to violin plots and error bars, as long as it wasn't a high variance distribution where they were trying to estimate the mean, which makes sense. Like if you have a lot of variance and you're trying to estimate the mean position of a mark, it's kind of hard. But the real reason we explored this technique, like I said, was to see how much better people did at effect size judgments, things like probability of superiority. And here we found that they actually did considerably better in this initial study. So we told them how to use the hypothetical outcome plots. We told them how to use the other visualizations or what they were seeing. And they did quite a bit better at making these probability judgments given 2 distributions or given 3 distributions. And so, I think one thing that's happening here in terms of perception is that we're relying on what we call ensemble processing ability of the visual system to actually intuitively estimate things like these summary statistics. And more vision science research is showing us that actually you don't even have to be consciously trying to count things when you see like a visual frequency encoding. And so I think that's partially why these are interesting, because they seem hard to deal with, but they're also relying on sort of these intrinsic abilities we have. But like I said before, we generally try to use different approaches to evaluate things. So this was sort of an initial just kind of perception study we did. We did another study that was a little bit more like perceptual decision making, where we were inspired by the New York Times use of hypothetical outcome plots to show the effects of sampling error in job estimates. So once a year, the jobs report comes out and journalists report on it. But they wanted to make the point that, even if you had like a steady growth trend in the economy, or even if you had, a steady growth trend, or even if you had no growth in the economy, you could end up, because of sampling error, seeing a jobs report that looked pretty different, that maybe made you think there was a trend when there wasn't, et cetera. And so we wanted to turn this into kind of an experiment to see, how much do these animated visualizations help over more conventional things like error bars. And so what we did is create a task where on each trial, the person in our study would see a set of noisy job estimates. So they'd see a hypothetical jobs report. And then they would have to basically assign an underlying model, which we framed it as assigning a headline to the jobs report. Where they saw these 2 possible growth models, so one with no growth and then one with steady growth. And then they saw the uncertainty from sampling error. And so we either showed them error bars, or we showed them hypothetical outcome plots. In another condition, we also showed them basically static frequency visualizations that were basically a bunch of lines showing hypothetical jobs reports if you sampled, say, 100 from this distribution. And in each case, they chose the one they thought was more likely, and then they gave us a confidence rating. And to analyze this data, we could have just had them do some number of these and then calculated accuracy. But we wanted to do something that gave us a little more information about sort of how sensitive people were to the information they get in a stimuli like this, using these different visualizations, error bars versus hops. And so we used a technique from graphical perception or psychophysics, which is called fitting psychometric functions, where basically we're fitting individual level logistic regressions to see how a person's kind of sensitivity or their accuracy changes as they get more information about which model is the right model. And so, here this difficulty or sensory evidence or amount of information that we're varying across the trials is the relative amount of support for, this being created by this model versus this model. And we also in the study had people do tasks. They got more stimuli that were sort of close to the point where this curve, their sort of response curve is kind of starting to change. So we use kind of a dynamic approach that gave them harder judgments as they did better, and gave them easier judgments as they did worse, to try to zero in on sort of their sensitivity. So to analyze these results, we then looked at these curves and used another sort of standard psychophysics measures, things like just noticeable difference, which is the amount of difference in the actual amount of information in the stimuli that you need to obtain a certain judgment accuracy. So we compared the just noticeable difference for hypothetical outcome plots to the just noticeable difference for things like error bars or these other static plots. One thing that was slightly surprising here was that nearly everyone did better with the hypothetical outcome plots. So this was within subjects. People did a block of trials with either error bars or hypothetical outcome plots, and then another block with them reversed. So this was kind of surprising that really nearly everyone did better. And to give some sense of the effect size here, someone who used hypothetical outcome plots could tell you with about 75% accuracy or more that this stimuli was more likely to convey a growth pattern, and this one was more likely to convey a no growth pattern, whereas someone who used something like error bars would be no better than chance at making this guess. The other surprising thing that we learned from this study about sort of this idea of animating uncertainty is that people who use the hypothetical outcome plots first before they use the error bars actually then did better with the error bars. So we estimated this kind of learning effect, and it existed if you used hypothetical outcome plots first, but the same was not true if you used error bars first. So something about sort of seeing this dynamic representation of the distribution, maybe has some value for helping people learn sort of an internal representation of what variation looks like in a model. Other sort of reason to use these things, of course, is that they're pretty generalizable. So, to animate uncertainty, all you're doing is taking draws from the underlying distribution, regardless of what sort of statistical model you used or what sort of data you used. You can look to, the statistical bootstrapping literature, and there's many different ways to resample your data. And so that means you can take a complex model and a complex visualization and still show uncertainty. If you imagine trying to add an error bar to something like a choropleth map or a cluster network diagram, et cetera, you can't really do it. And so one of the nice things about animated uncertainty is that it is generalizable. But of course, it can also be really controversial. So, some of you might remember 2016 election coverage where the night of the election, 538 rolled out this animated gauge where there were new results coming in every 30 seconds or so on election night. And so in between these sort of new inputs of data, they randomly sort of jittered the needle within a 50% confidence interval from the latest model as it's being updated. And people hated this. Many people election night just really hated this visualization. They called it irresponsible data journalism. But at the same time, you could look at the visualizations used to convey, the forecast leading up to the election, which gave you sort of these very clear probabilities, much easier to sort of suppress the uncertainty here. And nobody really complained about these. And so I think, here, I think the gauge is actually quite effective for making you contend with uncertainty. You really can't ignore it. But I think, because people are so hardwired to want to suppress uncertainty, you really do have to be careful sometimes with when you show it and how you show it. So I think, the problem here was not the visualization. It was that this was unrolled on election night when people were already very, very anxious, and they'd not had to really contend with uncertainty leading up to the election, or they were given visualizations that made it easier to suppress. So the final thing I want to briefly talk about for the next few minutes is just another example of sort of how uncertainty visualization can be complicated and how you have to deal with user psychology. And I really continue to learn new things as I do this type of research because of how complex I think this space is. So another recent study that I'll briefly just mention here was again related to this tendency people have to use these sort of simple visual judgments to substitute for probability judgments. So again, people tend to use things like the difference in means to estimate effect size. This is not a great heuristic, but it's much easier for people to use than to actually consider how to properly account for the uncertainty. And so we did a recent study where we wanted to look at just how strong these kind of strategies or these heuristics can be by seeing how people did with a visualization that didn't emphasize a mean and one that did. So we randomly assigned people in this study to visualization conditions that showed either 95% prediction or containment intervals, or hypothetical outcome plots, or probability density plots, or quantile dot plots. And they did 2 blocks of trials where in one trial they saw the visualization without a mean added, and in another trial they saw the visualization with a mean emphasized. And what we expected was that in some cases, maybe, adding the mean won't have a big effect because you can already sort of see where the mean is, even if it's not annotated in something like a density plot or quantile dot plot. But in some cases, like in particular hypothetical outcome plots, when you add the mean, you might actually change people's strategy, because now it's much easier for me to just look at the difference in means as sort of a function of the total y-axis range and sort of substitute that for my probability judgment. So that's what we wanted to look at. And we again asked people for these basically effect size judgments, probability of superiority, as well as actual decisions. So this experiment framed this as a fantasy sports game where you have to decide, do you want to invest in buying a new player or adding a new player to your team? The new player will help you score more. And the more you score, or if you score above a certain threshold, you win an award that's worth money, but you also have to pay for the new player. So it's kind of, again, trying to set up some realistic sort of incentives where people have to make this decision. Do I want to intervene or do I want to make this purchase? We also wanted to see, if you ask people what they're doing, what do they tell you? Because sometimes when we do these quantitative studies, we get a lot of information, but we can't exactly narrow down, exactly what did someone do. It's just a hard statistical identification problem. And so, we asked them for their strategies as well. And, here we learned again a lot, and some of it surprising. So we had expected to see some relatively big differences when we added the means to plots, like the hypothetical outcome plots. But we actually saw only a very small difference in how well people can make, for instance, these probability judgments with or without means. And this suggested to us that many people were actually just estimating the difference, the visual distance in means as a function of something like the y-axis range, whether or not we annotated it. So, so this is sort of a strong tendency to use these distance cues to substitute for effect size, because thinking about probability is hard. So we saw, for instance, that 80% of users relied on distance to judge effect size in some way, but only 8% of them also mentioned taking into account the variance or the uncertainty in those estimates. And so this is not, great in terms of people, are making us feel like people really understand the uncertainty visualizations we show them. We also found that the best visualization for judgments of perception was not the same as the best visualization for actual decisions. So people appear to process the same visualizations differently depending on what task they're doing, which is weird and hard to account for. But it's something we saw. And we also saw a lot of people switching strategies. So a lot of people, I think didn't quite know how to best use the visualization. So even with the same chart and the same task, they described how they tried out various strategies. Final thing that was surprising and really, made me think harder about just how hard it is to design visualizations that people won't misuse when it comes to uncertainty, was that, only the hypothetical outcome plots, these animated draws in this study, gave people the information they needed to answer the question, this probability of superiority question. Because all you had to do was see, how often do you see a swap in the order of the draws where the blue, suddenly does better than the red. What we saw, however, is that people did really badly with hypothetical outcome plots, even for this question where they were basically given really relevant information. So only about 16 of them reported using this strategy, which means the rest reported something like a function of visual distance between means. Which is exactly what we did not want them to do. Like that's the least efficient strategy, is to try to look at the moving lines and estimate the mean, and then look at the size of the distance between the means as a function of y-axis scale. So, so this really, made it hit home for me just how hard this is and how hardwired people are to suppress uncertainty. So just to conclude, simply presenting uncertainty is not enough. You have to think about it. I think visualizations of uncertainty should always try to avoid approaches that have these expressiveness problems. Things like error bars, are just really hard for people to make sense of. But we also want to avoid encodings like blur or opacity if we're trying to get people to actually make precise estimates, because they're just very hard to read. Frequency framing is one trick we found helps people better interpret uncertainty. And in some cases, when it's critical, you might want to use encodings like animation that make it hard to ignore. But as I just said, you have to sort of provide training, and you can't just assume, that people will get it. And finally, I think, the differences in cognitive load that we see in different experiments might be partially why we sometimes see these different results. So, depending how much someone's trying to keep in their head, how you convey uncertainty should potentially change. So I'll end there. A lot of the work I just presented, it was with some great collaborators. Alex Kao, for instance, led that last study. Matt Kay, I work with a lot. And so I just have to acknowledge that this is not all my work alone. So yeah, I'm happy to take questions now. Thanks for listening. So do I do the questions? Maybe. Should I just read them, perhaps?
People, please put your questions in the chat box.
So I can start answering them from the chat if that's the typical process. Sorry, I should have asked before. So someone asked if the optimal number of dots is relative to the area of the screen or the visualization. I think at some point, if you have like, say, a small display like we were working with, that is going to matter a lot. Like we had these mobile displays basically that people usually use on mobile phones, these transit displays. And so, like if you have a small screen, then you probably don't want to try 100 dots. Whereas if you have a huge display, maybe 100 dots is okay because people can still make them out. One thing I didn't mention, though, that I think really drives why smaller numbers of dots are sometimes better is this perceptual ability that the visual system has to do what's called subitizing, which is basically when we look at small counts of objects, usually like 4 or 5 or less, we don't even have to count them. We can just like automatically say that that's 3 dots or that's 4 dots. And so I think in this bus decision context we were looking at, like often people care about the tails of the distribution. And so I think small numbers of dots might work there regardless of your screen size, simply because people can easily recognize, that's 3 dots. Whereas if it was 15 dots, then they would actually have to count and it would make it more cumbersome to use. But yeah, that's a great question. Sure, I can provide slides. Somebody was asking. Somebody said, oh, for the difference, so a lot of my stuff was looking at differences between 2 distributions. Shouldn't we show people estimates of the difference? Yeah, that's a great question and a great point. I think, in a lot of cases, like in scientific literature, we might just show the difference. A lot of times in visualization, though, we're also trying to support as many estimates as possible with a single chart. So if you don't have unlimited space, I think a lot of the reasons we see things like error bars on separate distributions in, scientific visualizations or in the scientific literature even is that, you want to show the distributions themselves and you want to allow these sort of comparative judgments in a single visualization, and you can't show everything. So people make these sort of trade-offs. But yes, I mean, I think like when you show the difference distribution, as long as people understand that, you have helped them a lot. And you also then, the big problem with showing, 2 bars with error bars and asking people to compare them is often that people don't know the independence assumptions between the 2 distributions. So you can show the difference and you're automatically taking into account the whether or not those are correlated or not, say whether you have a within subject study or a between subject study. So yes, often you should try to show the difference. I think it's more abstract, and so a lot of lay people then might need a little more help interpreting in it. And again, sometimes you don't have enough space, but definitely you should be considering that. What are the biggest uncertainty problems or issues that still need solving? Asked by Doug Locke. That's a great question. It's not the same as where the research is headed, I would say. If I had to mention one, I would say that we're like in uncertainty communication research and specifically data visualization, which is what I do. We really sidestep the whole issue of epistemic uncertainty, or uncertainty that we can't really quantify, where in principle, we could know the true value if we had infinite information, as well as ontological uncertainty, as it's sometimes called, which I think of as more like specification uncertainty, which is like, how good is our model specification? We often can't quantify that. These types of uncertainty that we don't quantify, we don't know very much at all about how to express them well, in part because it's hard, there's no clear normative, answer for what someone should do with them because we can't quantify them. And I think that's what makes researchers like stay away. But I actually think that's one of the most important types of uncertainty. So things like presenting election forecasts, people get misled by the forecasts, not because the visualizations necessarily are horrible, but because those probabilities that the forecasts are spitting out are so dependent on all of the assumptions, and we can't quantify the uncertainty in those assumptions. But when we go to the election forecast page, those assumptions are not, conveyed necessarily front and center. And so a lot of what I recommend to people in a lot of cases is not just think about visualizing the uncertainty, but think about how you're going to acknowledge these harder to quantify uncertainties and really make people take them seriously. And so, yeah, I would not say that that's where the research is headed necessarily, but that's where I think it should head. There's a lot of research in uncertainty visualization right now in like the end user sort of machine learning context. So people using model predictions. It's making a lot of computer scientists who never thought about uncertainty visualization start to take it seriously. And I think that's also an important context, but again, not necessarily focused on hard to quantify uncertainty. So let me see. So Nick Costango asked, I think, about the hypothetical outcome plots. If the optimal strategy would have been to count the frequency of which output was superior, wouldn't that end up boiling down to a summary statistic? Yeah, I think it would. And that's, again, sort of similar answer to the previous question I had answered, where there's always, for anything we want to visualize, we can always boil it down to some set of statistics, but often we use visualization because we're trying to show the data and show people information about multiple things at once. And so yes, if we really only cared about this probability of superiority, we could just give people that probability. The problem is that people are, you have a bunch of people looking at charts for different reasons, and you often want the visualizations to support different judgments about individual probabilities as well, or individual random variables as well as combinations of them, et cetera. And so that's why we care about finding a visualization that conveys as many things as possible sort of effectively. So let's see. Have I tried using any of these techniques to teach intro level statistics? No, I haven't taught intro statistics, but I teach, basically intro statistics as part of some of my courses. But yeah, I guess I've used a little bit of this, not as much as I should, but there's definitely some alignment between what I know of like statistical pedagogy, like people who study how to teach statistics, and the kind of stuff I'm doing, and in particular simulation and animation. There's a few things I've seen from people who study basically stats education that have shown that those things are useful also. Usually they don't care about the visualization as much, but just the idea of simulation, but there's definitely some overlap. So any thoughts about dashboard design? Someone asked, how do we take some of these findings about visualizations for decision-making versus understanding and apply them to dashboard design? I've thought about dashboard design, but not necessarily as much about uncertainty communication in dashboard design. I think it's a really interesting question. I guess, in some ways it's maybe related to the stuff we did with arrival time estimates and for buses, where you kind of, in a dashboard, you want like a visualization that supports like glanceable estimates where, somebody's not going to have the time to study it. It's more for monitoring. And so, there, I think the frequency, the small numbers of dots, frequency representations like quantile dot plot could be effective. I've done some research on dashboards more related to other hard visualization questions related to dashboards, which is like where you have, the same data showing up in different visualizations in a dashboard, and often it's represented in very different ways, and there's a sort of a high cognitive load to trying to sort that out. So I guess as that applies to uncertainty, you would want to use similar uncertainty encodings across the whole dashboard, because learning even one encoding for probability is hard enough for people. But yeah, I think, dashboard design's an interesting area, and like I've done some other work, like I said, so definitely worth thinking more about. So someone asked, is there a clear visual hierarchy of encodings for uncertainty? And if so, how does it differ from the visual hierarchy for quantitative encoding? I think that's a great question. I think there's not a clear hierarchy. Part of what I was trying to get across in the latter part of my talk in particular is that it really does depend on the task. You know, I think a lot of the classic graphical perception stuff that ranks like what's the best encoding for, you know, reading values relies on a certain task, something like proportion judgment. In uncertainty, I think, I guess we could probably come up with a hierarchy for a specific task like probability estimation, but I still think these factors related to context end up mattering, like how much cognitive load is the person under, what's their level of statistical background. So I think it's kind of hard to come up with sort of a clear ranking or hierarchy for uncertainty. Let's see. How does one represent uncertainty of fat-tailed models like markets or pandemics? That's a good question. Yeah, I haven't thought about that as much. Maybe the person who asked it has an idea of why some of these approaches wouldn't work. There's definitely, you know, a lot of the uncertainty visualization approaches don't do well when you have things like extreme outliers. So for instance, with the hypothetical outcome plots, I was just randomly sampling draws from a distribution. So of course, if you have some sort of really skewed distribution, that's gonna not work as well. But you could just do what we did similar to the quantile dot plots where you try to sample proportional to quantiles, but still outliers can throw things off. Yeah, I'd have to think more about the fat-tailed question, how that intersects with the uncertainty visualization. It's interesting question. My surprise, someone asked if I could speak a little more about my surprise that different visualizations are better for judgment versus decisions. Yeah, I think the reason, I mean, I think maybe I shouldn't be surprised because, you know, everything is like people's behavior is always more complex than you think. But I think when we try to sort of dissect how someone should make a decision, it's like the most natural intuition is that first they make a probability estimate and then they try to decide like how much do I care about these stakes. And so in the kind of studies we're doing, we're trying to set up sort of a pretty level playing field where people's individual things like tolerance for risk should have a minimal effect so that we should be able to say, you know, this is really the optimal decision. And so in that context, it's weird to me that, you know, the thing that helps you best estimate the probabilities that you should need to make the decision is different. But yeah, maybe that's not as surprising as it sounds, or maybe that's more expected. So somebody asked, does using audio, one of the last questions, does using audio for audio tones to represent hypothetical outcomes work? That's an area that I think more and more people in visualization research are starting to look at. I don't know off the top of my head, but there's a lot of interest lately in things like accessibility, where a lot of people, you know, way more than we expect, have different types of visual impairments. And so using audio becomes pretty important. There's some research, I don't know that anybody's done anything with trying to convey like distribution with audio. I think it's been a little simpler, but that's a great question. Oh, someone related final thing. Someone I think followed up on the question about fat-tailed models is log scales. Yeah, I don't know that I have a good answer for that. I'd have to think about it more. So yeah, sorry, no easy answer for me. Thank you all for these questions. This was really fun. I'm gonna stop sharing my screen. So yeah, I'll let Naomi close, I guess. Thank you everyone for coming and asking me great questions.
Hello, everybody. Thank you for coming. Here, let me put my video back on. Thank you for coming. Thank you, Jessica, so much for your wonderful talk. Thank you, Cameron, for hosting us once again. And I will post our next meeting in the next few days. I have the information. Again, it will be February 10th with Ben Jones talking. And with that, and thanks to everybody for coming, the speaker, the host, we're done.
Thanks so much, Naomi.